Right now, at this very moment, you're hurtling through space at nearly 67,000 miles per hour. You're riding on a pale blue dot that's spinning through an endless cosmic dance, surrounded by neighbors both familiar and utterly alien. Yet for all our telescopes, all our spacecraft, all our centuries of gazing upward, our solar system remains beautifully, mysteriously incomplete to us. Welcome to Sleep About Science. Tonight we're exploring 100 secrets our solar system has never revealed, as mysteries that float just beyond our understanding, waiting in the quiet darkness between worlds. And if you drift off to sleep while listening, that's perfectly wonderful. Sometimes the most profound mysteries are best contemplated in that gentle space between waking and dreams. Before we begin, please make yourself comfortable wherever you are in the world. Pull up your blankets, adjust your pillows, and let yourself settle in. And remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into the cosmos. Now let's begin with something that might surprise you. Despite all our space missions, despite the Voyagers and Cassinis and countless robotic explorers, we've physically visited less than 1% of our solar system. Think about that for a moment. In your own neighborhood, bookless collection of planets and moons and asteroids and comets that we call home, mine, we're still strangers to nearly everything around us. The first mystery lives right here, beneath your feet. Deep in Earth's core, something extraordinary is happening that we've never fully understood. Every few 100,000 years, our planet's magnetic field weakens, wobbles, and sometimes completely flips. North becomes south, south becomes north. We know this happens. We can see it recorded in ancient rocks like pages in a cosmic diary. But we don't know why. We don't know when it will happen next. And we don't know what it would mean for life on Earth when it does. Imagine the invisible shield that protects us from solar radiation simply switching direction. Scientists have theories, of course. They speak of dynamo effects and convection currents in molten iron, of complex interactions between Earth's rotation and its liquid outer core. But theories aren't certainties. The truth is, we live under the protection of a magnetic field we don't truly comprehend. But the mystery deepens. Recent studies suggest that Earth's magnetic field isn't just flipping, it's weakening overall. Over the past 160 years, the field has lost about 10% of its strength. Some regions, particularly over the South Atlantic, show such pronounced weakening that satellites passing through the area experience glitches from increased radiation exposure. Scientists call this the South Atlantic anomaly, and it's growing larger and weaker each year. What's causing this weakening? Is it a prelude to a full magnetic reversal? Could our planet's protective shield fail entirely for a period of time? The geological record suggests that during past reversals, the magnetic field doesn't just flip instantly. It can take thousands of years to complete the transition, during which time the field might be chaotic, weak, or even temporarily absent. Consider what this might mean. Without a strong magnetic field, our atmosphere would be vulnerable to being stripped away by solar wind, much like what happened to Mars billions of years ago. Electronic systems would be vulnerable to radiation damage. The beautiful auroras that dance at our poles might appear everywhere, but as a sign of atmospheric destruction rather than natural beauty. And here's something even more unsettling. We don't know if magnetic reversals have affected life on Earth in the past. Some scientists suggest that periods of weak magnetic fields might have coincided with mass extinction events, though the evidence remains inconclusive. Others propose that magnetic reversals might have actually accelerated evolution by increasing cosmic ray exposure and genetic mutation rates. Moving outward from our mysterious home, we encounter our familiar companion, the Moon. You might think we understand our Moon quite well. After all, 12 humans have walked on its surface, we've mapped its face, we've studied its rocks, but the Moon holds secrets that would astonish you. For instance, the Moon is slowly drifting away from us. Right now, as you listen to this, our lunar companion is moving approximately 1.5 inches farther from Earth every year. Eventually, in the distant future, it will appear smaller in our sky. Eventually, total solar eclipses will become impossible. The Moon that has inspired poets and lovers and dreamers throughout human history is quietly saying goodbye so slowly that no human lifetime could notice. But why? We know tidal forces are involved. We can measure the Moon's retreat precisely, but the deeper mechanics of this cosmic farewell remain beautifully complex. And here's something even more intriguing. The Moon influences our planet in ways we're still discovering. It stabilizes our axial tilt. It drives our tides. It may have been crucial to the development of life itself, yet we don't know exactly how it formed. The prevailing theory suggests a Mars-sized object called Theia crashed into early Earth about 4.5 billion years ago, and from that violent collision, our moon was born. But this is still just our best guess about our closest celestial neighbor. The chemical composition of moon rocks supports this theory in some ways, but challenges it in others. The moon and Earth have remarkably similar isotopic compositions, more similar than they should be if the moon formed from the debris of an impacting foreign object. Recent computer simulations suggest the collision might have been even more dramatic than we imagined. Some models propose that the impact temporarily turned Earth into a molten donut-shaped mass called a synestia, from which both Earth and Moon recondensed. Other models suggest multiple smaller impacts rather than one giant collision. The truth is, we're still piecing together the violent birth story of our nearest neighbor. The Moon's far side, often mistakenly called the dark side, holds its own mysteries. It's more heavily cratered than the side we see. Its crust is thicker, and it contains geological features that don't match what we observe on the near side. Chinese spacecraft have begun exploring this hidden hemisphere, but every discovery seems to raise new questions rather than answer old ones. Why is the far side so different? Some scientists propose that early in the Moon's history, a second, smaller moon orbited Earth alongside our current moon. Eventually, this companion moon collided with the far side of our moon at relatively low speed, creating the thicker crust and different terrain we observe today. But this big splat theory, while intriguing, remains unproven. And here's something that might keep you wondering as you drift towards sleep. The moon's relationship with Earth creates a resonance that affects everything from biological rhythms to ocean currents. Yet we still don't fully understand how this ancient dance between world and moon shapes life itself. Studies have found correlations between lunar cycles and everything from coral spawning to human sleep patterns, but the mechanisms remain mysterious. Recent discoveries have revealed that the moon isn't the dead, static world we once thought. Lunar seismometers left by Apollo astronauts detected moonquakes that continue to this day. Some of these quakes occur in regular cycles related to Earth's gravitational pull, but others seem random and unexplained. The moon also experiences mysterious transient lunar phenomena minus brief flashes of light and color, observed by Earth-based astronomers for centuries but never fully explained. Water on the moon presents another puzzle. We now know that water ice exists in permanently shadowed craters at the lunar poles, but we don't know how it got there or how much exists. Some estimates suggest billions of tons of water ice scattered across the lunar surface, locked away in places where sunlight has never touched the ground for billions of years. This lunar water could be crucial for future human exploration, but its origin remains debated. Did comets deliver it? Did it form from hydrogen ions in the solar wind combining with oxygen in lunar rocks? Could some of it have been present since the moon's formation? Each possibility has different implications for how much water exists and how difficult it might be to extract and use. Moving outward through our solar system, we encounter Venus, our nearest planetary neighbor, and perhaps our most misunderstood sibling. Venus spins backward compared to most planets, rotating so slowly that a Venusian day is longer than a Venusian year, but we don't know why. Something in Venus's past, perhaps a massive collision, perhaps complex gravitational interactions, caused this backwards rotation. The planet keeps its secret locked beneath clouds of sulfuric acid. Those clouds themselves present another mystery. Venus's atmosphere is nearly 100 times denser than Earth's, creating a runaway greenhouse effect that makes the surface hot enough to melt lead. But the upper atmosphere, where those mysterious clouds swirl, is actually quite temperate. Some scientists have speculated that life might exist there, floating in those acidic clouds like microscopic balloons. Recent detections of phosphine gas minus a potential biosignature have only deepened the mystery. On Earth, phosphine is produced almost exclusively by living organisms or industrial processes. Finding it in Venus's atmosphere was completely unexpected and has sparked intense scientific debate. Subsequent studies have questioned whether phosphine is actually present, but the controversy has renewed interest in the possibility of life in Venus's clouds. The surface of Venus presents its own collection of mysteries. Despite being shrouded in dense clouds, radar mapping from spacecraft has revealed a world of vast plains, towering mountains, and evidence of intense volcanic activity. But the pattern of volcanism on Venus doesn't match what we see on Earth or other rocky planets. Venus appears to have experienced global resurfacing events, periods when the entire planet's surface was renewed through massive volcanic activity. The surface we see today is relatively young, perhaps only 300 to 800 million years old, suggesting that something catastrophic wiped away all older features. But we don't know what triggered these global resurfacing events or whether they continue today. Some scientists propose that Venus's thick atmosphere prevents the planet from cooling efficiently, leading to periodic episodes where heat builds up until the entire crust becomes unstable and melts. Others suggest that the planet's lack of plate tectonics causes heat to accumulate until it's released in massive volcanic outbursts. But these remain theories, and the actual mechanism of Venus's geological evolution remains mysterious. Venus also shows us something unsettling about planetary evolution. Earth and Venus began quite similarly, similar size, similar distance from the Sun, similar composition, yet one world became a garden, the other an inferno. Understanding exactly how and why Venus became what it is might be crucial to understanding our own planet's future and the fate of Earth-like planets elsewhere in the galaxy. The question of why Venus has no moons also puzzles astronomers. Earth has one large moon, Mars has two small ones, and the giant planets have dozens or hundreds of moons each. But Venus, despite its substantial size and gravitational pull, orbits alone. Did Venus once have moons that were somehow lost? Does its backward rotation relate to this apparent lack of natural satellites? The answers remain elusive. Mars, the red planet that has captured our imagination for centuries, holds perhaps more mysteries than any other world in our solar system. We know Mars once had flowing water. We can see the ancient riverbeds, the dried lake shores, the evidence of an ocean that may have covered much of its northern hemisphere. But where did all that water go? Some of it froze at the poles, some of it escaped to space, but vast amounts seem simply to have vanished. Recent discoveries suggest that much of Mars's water might be locked away underground, trapped in mineral structures we're only beginning to understand. The planet might be far wetter than we ever imagined, but in forms and places we never expected. Ground-penetrating radar on Mars-orbiting spacecraft has revealed what appear to be massive underground reservoirs of water ice, and possibly even liquid water, scattered across the planet. Some of these deposits are enormous individual ice sheets that could contain more water than some of Earth's Great Lakes. But we don't know how this water got there, how long it's been there, or whether it moves and changes over time. And then there's the question that keeps astrobiologists awake at night. Did life ever exist on Mars? We've found organic molecules. We've found evidence of past habitability. We've even found seasonal methane emissions that could suggest ongoing biological processes. But we haven't found life itself. Every rock sample, every atmospheric reading, every photograph from our rovers and orbiters adds to the tantalizing possibility without providing definitive proof. The methane mystery is particularly intriguing. Earth's atmosphere contains methane primarily because living organisms produce it, so finding methane on Mars was exciting, but the methane appears and disappears in ways that don't match our understanding of atmospheric chemistry. Sometimes it's present in detectable quantities, sometimes it's completely absent, and we can't predict when or where it will appear. If the methane isn't biological, what produces it? Geological processes can create methane, but they typically produce it continuously rather than in sporadic bursts. Impact events could release methane from subsurface deposits, but we haven't observed impacts that correlate with methane detections. The mystery deepens with each new measurement. Mars also presents us with geological mysteries that challenge our understanding of planetary physics. Olympus Mons, the largest volcano in the solar system, rises 13.6 miles above the Martian surface, nearly 3 times the height of Mount Everest. But unlike Earth's volcanoes, which form chains as tectonic plates move over hotspots, Olympus Mons appears to have grown in place for hundreds of millions of years. This suggests Mars might not have plate tectonics as we understand them, but we don't know why. Plate tectonics on Earth helps regulate our planet's temperature and may be crucial for maintaining habitability over geological time. The absence of plate tectonics on Mars might explain why the planet lost its magnetic field and much of its atmosphere, but the relationship between these processes remains unclear. The Martian dichotomy, the dramatic difference between the heavily cratered southern highlands and the smooth northern lowlands, presents another puzzle. The northern lowlands sit several miles lower than the southern highlands, and the boundary between them is one of the sharpest features on the planet. Some scientists propose that a massive impact created this dichotomy, while others suggest it formed through internal geological processes. Recent evidence for a possible ancient ocean in the northern lowlands adds another layer to this mystery. Mars's 2 small moons, Phobos and Deimos, are themselves mysterious objects. They're irregularly shaped and appear to be captured asteroids, but their orbits are nearly circular and aligned with Mars's equator minus characteristics that don't match what we'd expect for captured objects. Phobos, the larger moon, is spiraling slowly inward and will eventually either crash into Mars or break apart to form a ring system. But Phobos holds its own secrets. Its surface is covered with mysterious grooves that appear to radiate from the largest crater on the moon. Some scientists propose these grooves formed during the impact that created the crater, while others suggest they're stress fractures caused by tidal forces from Mars. Recent studies hint that Phobos might not be a captured asteroid at all, but rather material that was blasted off Mars by an ancient impact and later reaccreted into a moon. The asteroid belt between Mars and Jupiter contains millions of rocky fragments, remnants of the solar system's formation, perhaps pieces of a planet that never quite formed. But even this seemingly simple collection of space rocks holds mysteries. Some asteroids are rich in water and organic compounds, suggesting they might have been the source of Earth's oceans and perhaps even the building blocks of life. Others contain metals and minerals in concentrations that could revolutionize human industry, if we could ever figure out how to mine them. The asteroid belt itself is far more complex than it initially appeared. Rather than being a uniform collection of similar objects, it contains distinct families of asteroids with different compositions, sizes, and orbital characteristics. Some asteroids are solid rocks. Others appear to be loosely bound piles of rubble held together by weak gravity. Some rotate rapidly, others tumble chaotically through space. Ceres, the largest object in the asteroid belt, was recently explored by NASA's Dawn spacecraft, and the discoveries were startling. Bright spots on Ceres's surface turned out to be salt deposits, suggesting this dwarf planet has mined or recently had Messic's liquid water beneath its surface. Some scientists now believe Ceres might be more like an ocean world than a simple asteroid, hiding a subsurface sea that could potentially harbor life. The bright spots on Ceres appear to be primarily sodium carbonate, a type of salt that forms when water containing dissolved carbon dioxide evaporates. But the presence of these salts raises questions about the chemistry and temperature of Ceres's subsurface ocean. How long has liquid water existed beneath Ceres's surface? What keeps it liquid in the cold depths of the asteroid belt? Could this distant dwarf planet harbor the chemical conditions necessary for life? Dawn also discovered organic compounds on Ceres's surface, Midas complex carbon-based molecules that are the building blocks of life as we know it. These compounds appear to be native to Ceres rather than delivered by impacts, suggesting that organic chemistry might be common throughout the asteroid belt. This discovery has implications for understanding how organic compounds formed and spread throughout the early solar system. But perhaps most mysteriously, Ceres shows evidence of ongoing geological activity. The dwarf planet has a surprisingly young surface with few impact craters, suggesting that some process is continually renewing its appearance. Water vapor has been detected escaping from Ceres's surface, possibly through cryovolcanic activity. Jupiter, the king of planets, dominates the outer solar system with its enormous mass and gravitational influence. But Jupiter holds secrets that challenge our most basic assumptions about how planets form and behave. The Great Red Spot, a storm larger than Earth that has been raging for centuries, is slowly shrinking. We don't know why. We don't know if it will disappear entirely or somehow regenerate. We're watching a weather phenomenon that has persisted longer than human civilization, and we can't predict its future. The Great Red Spot has shrunk by more than half since the late 1800s, when it was large enough to fit 3 Earths inside it. Today, it could barely contain 1 Earth, and the rate of shrinkage appears to be accelerating. Computer models of the storm's dynamics can't explain why it's contracting or predict whether it will continue shrinking until it disappears. But the Great Red Spot isn't Jupiter's only mysterious storm. The planet hosts dozens of other long-lived storms, including white ovals and smaller red spots that appear and disappear over periods of years or decades. Some of these storms merge with each other in dramatic events that can be observed from Earth, but we don't understand the processes that control these mergers or the energy sources that sustain the storms for such long periods. Jupiter's interior remains largely mysterious despite decades of study. The Juno mission has revealed that the planet's core isn't the solid, well-defined structure we expected, but rather a fuzzy or dilute core that extends much farther out than models predicted. Jupiter might not have formed the way we think planets form. It might have begun as a much more complex process of gravitational accumulation and interaction than our theories suggest. The fuzzy core discovery has forced scientists to reconsider fundamental assumptions about planetary formation. If Jupiter's core is dilute and extended, It suggests the planet might have formed through a different process than the traditional model of solid core accretion followed by gas capture. Some new models propose that Jupiter formed through gravitational instability, a process where the giant planet condensed directly from the solar nebula without first forming a solid core. Jupiter's magnetic field is another source of mystery. It's the strongest planetary magnetic field in the solar system, nearly 20,000 times stronger than Earth's. But the field has an unusual structure that doesn't match simple models of planetary magnetism. Recent measurements by Juno have revealed that the magnetic field is surprisingly complex and irregular, with features that vary on surprisingly small scales. The source of Jupiter's powerful magnetic field appears to be different from Earth's. While Earth's field is generated by convection in a liquid iron core, Jupiter's field might be generated by metallic hydrogen mass, a strange form of matter that exists only under the extreme pressures found deep within giant planets. But we've never been able to create or study metallic hydrogen in laboratory conditions, so our understanding of its properties remains theoretical. And then there are Jupiter's moons, Natis solar system, unto themselves. Europa, with its icy surface hiding a global ocean, might be one of the most likely places to find life beyond Earth. But that ice shell is far more complex than we initially realized. The surface shows evidence of active geology, of material exchanging between the ocean below and space above. Yet we don't understand the mechanisms that drive this activity. Europa's ice shell appears to be relatively thin in some places, perhaps only a few miles thick, and much thicker in others. This variation in thickness affects how easily material can exchange between the surface and the subsurface ocean, which in turn affects the chemistry available for potential life. But we don't know what controls these variations in ice thickness or how stable they are over time. The surface of Europa is crisscrossed by linear features called linear minus cracks and ridges that appear to be related to tidal stresses from Jupiter's gravity. But the detailed formation mechanisms of these features remain mysterious. Some appear to be places where the ice shell has cracked and separated, allowing warm water from below to freeze in the gap. Others might be pressure ridges where ice has been compressed and pushed upward. Recent studies suggest that Europa's ocean might be more Earth-like than we initially realized. The ocean appears to be in direct contact with Europa's rocky mantle, allowing for complex chemical interactions that could provide energy sources for life. The ocean might also be mildly acidic, similar to some Earth environments where life thrives. But we don't know the detailed chemistry of Europa's ocean or how it compares to the conditions where life first arose on Earth. Io, Jupiter's volcanically active moon, presents another puzzle. Its surface is constantly being reshaped by sulfur-spewing volcanoes, powered by tidal heating from Jupiter's gravity. But the intensity and distribution of Io's volcanism doesn't quite match our theoretical models. The moon is more geologically active than we can fully explain, suggesting there might be additional energy sources or mechanisms at work. Io's volcanoes produce some of the most dramatic eruptions in the solar system, with plumes of sulfur and sulfur dioxide reaching hundreds of miles above the surface. Some eruptions are so powerful they can be detected by Earth-based telescopes, but the timing and location of these eruptions often seem random, making it difficult to predict when and where the next major eruption will occur. The composition of Io's volcanic emissions also presents mysteries. While most volcanoes emit sulfur compounds, some appear to erupt silicate lavas similar to those found on Earth. The temperature of these silicate eruptions can exceed 2,000 degrees Fahrenheit, much hotter than typical volcanic activity on Earth. We don't know why Io's volcanoes reach such extreme temperatures or how the moon's interior can generate such intense heat. Ganymede, the largest moon in the solar system, has its own magnetic field, something we didn't expect for a moon. This magnetic field suggests Ganymede might have a liquid iron core, making it more planet-like than moon-like in some ways. It also likely has a subsurface ocean, making it another potential harbor for life in the outer solar system. But Ganymede's magnetic field is unusual. Unlike planetary magnetic fields, which are typically dipolar like a bar magnet, Ganymede's field has a complex structure that suggests it might be generated by a different mechanism than we understand. The field also interacts with Jupiter's much stronger magnetic field in ways that create auroras at Ganymede's poles, the first auroras ever observed on a moon. The subsurface ocean of Ganymede might be one of the largest bodies of liquid water in the solar system, possibly containing more water than all of Earth's oceans combined. But this ocean exists in a complex layered structure, with multiple layers of ice and water stacked on top of each other like a frozen sandwich. We don't understand how these layers formed or how they interact with each other. Callisto, the outermost of Jupiter's large moons, presents its own mysteries. Its surface is one of the most heavily cratered in the solar system, suggesting it's very old and geologically inactive. But recent studies suggest Callisto might also have a subsurface ocean, despite its apparent lack of geological activity. How could such an old, cold world maintain liquid water beneath its surface? The answer might lie in Callisto's composition and structure. Unlike the other large moons of Jupiter, Callisto appears to be only partially differentiated. It's a mixture of rock and ice rather than having distinct layers. This structure might allow for different heat retention and transfer mechanisms that could maintain a subsurface ocean even without strong tidal heating. Saturn, with its magnificent ring system, might seem like a solved mystery. After all, we've studied those rings extensively with ground-based telescopes and spacecraft. But the Cassini mission revealed that Saturn's rings are far more dynamic, complex, and mysterious than we ever imagined. They're not the ancient, stable structures we once thought, but rather relatively young features that are constantly changing, constantly being created and destroyed by processes we don't fully understand. The age of Saturn's rings has been hotly debated for decades. Recent analysis of Cassini data suggests the rings might be only 10 to 100 million years old, extremely young compared to the 4.5 billion-year age of the solar system. If this estimate is correct, it means Saturn's rings formed relatively recently and might be temporary features that will disappear in the future. But how did such young rings form? One possibility is that a moon or large asteroid wandered too close to Saturn and was torn apart by tidal forces. Another possibility is that collisions between existing moons created the debris that became the rings. Some scientists even propose that the rings might be constantly renewed through ongoing processes, making their apparent young age misleading. The rings contain spokes, many as dark streaks that appear and disappear on timescales of hours. They're somehow related to Saturn's magnetic field and the charged particles trapped within it, but the exact mechanism remains elusive. The spokes were first observed by the Voyager spacecraft and later studied in detail by Cassini, but despite decades of observation, we still don't understand how they form or why they appear in certain locations and not others. The rings also contain propeller-shaped disturbances created by tiny moonlets embedded within them, but we don't know how many such moonlets exist or how they formed. These propeller features appear as gaps and density waves in the ring material, created by the gravitational influence of moonlets too small to be directly observed. The discovery of these features suggests that Saturn's rings contain a population of small moons that we're only beginning to understand. The structure of Saturn's rings is incredibly complex, with thousands of individual ringlets and gaps controlled by gravitational resonances with Saturn's moons. Some gaps are kept clear by small shepherd moons that orbit within or near the rings, while others are maintained by resonances with more distant moons. But the detailed mechanisms that create and maintain this structure remain incompletely understood. Saturn's moon Enceladus has become one of the most exciting worlds in our solar system since Cassini discovered jets of water vapor shooting from its south polar region. These jets suggest a liquid ocean beneath Enceladus's icy surface, and chemical analysis of the jets has revealed organic compounds and energy sources that could potentially support life. But we don't understand the internal structure that maintains this subsurface ocean or the mechanism that powers those dramatic jets. The south polar region of Enceladus is unusually warm and geologically active, featuring long cracks in the ice called tiger stripes from which the jets emerge. But the north polar region is heavily cratered and appears ancient and inactive. This dramatic dichotomy between the two hemispheres is unprecedented among icy moons and remains unexplained. Recent analysis of Cassini data suggests that Enceladus's ocean might be in direct contact with the moon's rocky core, allowing for complex chemical reactions that could provide energy for life. The ocean appears to be alkaline and contains hydrogen gas minus both characteristics that could support certain types of microorganisms known on Earth. But we don't know the detailed chemistry of Enceladus's ocean or how it compares to environments where life thrives on Earth. The jets of Enceladus vary in intensity over time, possibly related to tidal stresses from Saturn's gravity. When Enceladus is farthest from Saturn in its elliptical orbit, the jets are strongest, suggesting that the cracks in the ice open and close as the moon is stretched and compressed by tidal forces. But the timing and intensity of these variations don't perfectly match theoretical predictions, suggesting additional factors are involved. Titan, Saturn's largest moon, is perhaps the most Earth-like world we know of, despite being utterly alien. It has weather, it has seasons, it has lakes and rivers and rain, but instead of water, All of this is methane and ethane operating at temperatures so cold that water would be as hard as rock. Titan's thick atmosphere and active weather cycle create an environment we're still struggling to understand. Titan's atmosphere is primarily nitrogen, like Earth's, but it also contains several percent methane. This methane plays the same role on Titan that water vapor plays on Earth. It evaporates from surface lakes, forms clouds, and precipitates as rain. But methane should be broken down by sunlight over relatively short periods of time, so there must be some process continuously replenishing Titan's atmospheric methane. The source of Titan's methane remains one of the Moon's greatest mysteries. Possible sources include outgassing from the interior, impact delivery from comets, or even biological processes in a subsurface ocean. Recent studies suggest Titan might also have a subsurface water ocean, making it both an alien hydrocarbon world on the surface and a potentially habitable water world beneath. The interaction between these two very different chemical systems, surface hydrocarbons and subsurface water, could create possibilities for life that we've barely begun to contemplate. Could there be two completely different biospheres on Titan, one based on water chemistry and another based on hydrocarbon chemistry? The possibility seems like science fiction, but it's within the realm of scientific possibility. Titan's surface features include vast sand dunes made of organic particles, river valleys carved by liquid methane, and lakes filled with liquid hydrocarbons. Some of these lakes are larger than the Great Lakes of North America, and they show evidence of shoreline features, seasonal changes, and even what might be waves. But the detailed processes that shape Titan's surface remain poorly understood. The organic chemistry on Titan is incredibly complex, producing a variety of molecules that rain down onto the surface and accumulate over geological time. This organic material might be similar to the prebiotic compounds that existed on early Earth before life arose. Studying Titan's chemistry could provide insights into the chemical processes that led to the origin of life on our own planet. Moving to the edge of our solar system, we encounter Uranus and Neptune, the ice giants that remain among the least understood worlds in our celestial neighborhood. Uranus rotates on its side, tilted at 98 degrees relative to its orbital plane. Something in its past, likely a massive collision, knocked this world over, but we don't know what or when. Uranus also has a magnetic field that's tilted 59 degrees from its rotational axis and doesn't originate from the planet's center. This suggests its interior structure is far stranger than we've assumed. The extreme tilt of Uranus affects everything about the planet's behavior. Its seasons last 21 Earth years each, with each pole experiencing decades of continuous sunlight followed by decades of darkness. This extreme seasonal cycle should create dramatic atmospheric changes, but Uranus shows surprisingly little seasonal variation in its appearance or temperature distribution. Uranus's magnetic field is not only tilted but also offset from the planet's center by about 1/3 of the planet's radius. This unusual configuration suggests that the magnetic field might be generated in a shell layer rather than in the planet's core, but we don't understand the mechanism that could create such a field. The magnetic field also varies significantly in strength and direction as the planet rotates, creating a complex magnetosphere unlike any other in the solar system. The composition and structure of Uranus's interior remain largely mysterious. The planet is called an ice giant because it's thought to contain large amounts of water, methane, and ammonia ices, but we don't know the detailed distribution of these materials or how they interact. The planet's relatively low density suggests it's less compressed than we might expect, possibly indicating an unusual internal structure. Uranus has a faint ring system that was discovered only in 1977, just 2 years before Voyager 2's visit. These rings are much darker and narrower than Saturn's rings, and they're composed of material that reflects only a few percent of incident sunlight. We don't know what this dark material is or how the rings formed and evolved. Neptune, discovered through mathematical prediction rather than direct observation, holds its own mysteries. It radiates 2.6 times more energy than it receives from the Sun, suggesting an internal heat source we don't fully understand. Its largest moon, Triton, orbits backward and shows signs of recent geological activity despite being so far from the Sun that temperatures hover around -390 degrees Fahrenheit. Neptune's excess heat is particularly puzzling because Uranus, despite being closer to the Sun, doesn't show significant internal heat. Both planets should have similar formation histories and internal structures, so why does Neptune have such a strong internal heat source while Uranus doesn't? Some theories propose that Neptune experienced a massive impact early in its history that deposited energy that is still being radiated away, but this remains speculative. Triton might be a captured Kuiper Belt object, but we don't know how Neptune managed to capture such a large moon without destroying it. The capture process should have been incredibly violent, likely involving multiple gravitational encounters and energy dissipation mechanisms we don't fully understand. Triton's retrograde orbit and tilted orientation support the capture hypothesis, but the details remain mysterious. Triton shows evidence of nitrogen geysers, plumes of nitrogen gas and dark particles erupting from its surface and reaching heights of several miles. These geysers are powered by solar heating of subsurface nitrogen ice, but the mechanism that concentrates solar energy enough to drive these eruptions on such a cold world is not well understood. Both ice giants likely have diamond rain in their atmospheres, pressures and temperatures that compress carbon into crystalline structures that then sink toward the planetary cores. Laboratory experiments have confirmed that diamond formation is possible under the conditions expected in these atmospheres. But we can't be certain of this process, and we don't know what it means for the planet's internal structure and evolution. The atmospheric dynamics of both Uranus and Neptune remain poorly understood. Neptune has the fastest winds in the solar system, with speeds reaching up to 1,200 miles per hour, despite receiving only 1,000th as much solar energy as Earth. What drives these incredibly fast winds on such a cold, distant world? Uranus, despite its extreme seasonal cycle, shows much less atmospheric activity than Neptune. Why are these similar planets so different in their atmospheric behavior? The outer reaches of our solar system hold perhaps the deepest mysteries of all. The Kuiper Belt, that region beyond Neptune populated by icy worlds and comets, is far more complex and dynamic than we initially realized. Pluto, now classified as a dwarf planet, revealed its secrets when New Horizons flew past in 2015. Instead of the dead, cratered world many expected, Pluto showed evidence of recent geological activity, complex atmospheric dynamics, and a surprisingly diverse surface. Pluto's surface features include vast plains of nitrogen ice, towering mountains of water ice, and complex terrain that suggests active geological processes. But how can a world so small and cold maintain geological activity? Pluto receives only 1/1600th as much sunlight as Earth, and its small size means it should have lost its internal heat long ago. Yet the smooth plains and young surface features suggest that Pluto has been geologically active within the past few million years. The heart-shaped feature on Pluto, informally named Tumbor Regio, appears to be a vast plain of nitrogen ice that convects and flows like a slow glacier. Computer models suggest this nitrogen ice undergoes convection cycles that last hundreds of thousands of years, constantly renewing the surface and erasing impact craters. But the energy source that drives this convection remains unclear. Pluto's atmosphere is another source of mystery. Despite its small size and cold temperature, Pluto has a surprisingly extensive atmosphere composed primarily of nitrogen with traces of methane and carbon monoxide. This atmosphere extends much farther from the surface than theoretical models predicted, and it appears to be escaping to space at a rate that would deplete it over geological timescales. But Pluto's moon Charon presents an even deeper mystery. It's unusually large relative to Pluto Nu. The two worlds almost form a double planet system, orbiting around a common center of mass. We don't know how such a system formed. The most likely explanation involves a massive collision early in solar system history, but the details remain elusive. Charon shows its own evidence of geological activity, including a vast canyon system that extends across much of the Moon's visible hemisphere. This canyon might have formed as Charon's subsurface ocean froze and expanded, cracking the surface. But the presence of a subsurface ocean on such a small, cold world would require heat sources we don't fully understand. Beyond the Kuiper Belt lies the Oort cloud, a theoretical spherical shell of icy objects that might extend halfway to the nearest star. We've never directly observed the Oort cloud in Realm. It's too distant and its objects too faint, but we infer its existence from the long-period comets that occasionally dive into the inner solar system. How many objects are in the Oort cloud? How did they get there? What triggers them to begin their million-year journeys toward the Sun? These questions remain beautifully unanswered. The Oort cloud might contain trillions of icy objects, representing a vast reservoir of primordial material from the early solar system. But the cloud's structure and dynamics remain largely theoretical. Some models suggest it has distinct regions with different populations of objects, while others propose a more uniform distribution. The gravitational influence of passing stars and galactic tides might disturb Oort cloud objects and send them toward the inner solar system, but we don't understand the detailed mechanisms of these processes. Recent discoveries have revealed that our solar system is far stranger than we ever imagined. Objects like Sedna, a dwarf planet with an orbit so elongated and distant that it takes over 11,000 years to complete one revolution around the Sun, suggest there might be undiscovered massive objects in the outer solar system, perhaps even a ninth planet lurking in the darkness beyond our current detection capabilities. Sedna's orbit is so unusual that it can't be explained by gravitational interactions with the known planets. Its closest approach to the Sun is still farther than Neptune's orbit, and its farthest point is nearly 1,000 times Earth's distance from the Sun. Some astronomers propose that Sedna's orbit was shaped by a close encounter with another star billions of years ago, while others suggest it's evidence of an undiscovered planet in the outer solar system. The hypothetical planet 9, if it exists, would be approximately 10 times more massive than Earth and orbit at distances 20 times farther than Neptune. Its gravitational influence might explain the unusual clustering of orbits we observe in extreme trans-Neptunian objects. But despite extensive searches using some of the world's most powerful telescopes, we haven't found direct evidence of this world. The search for Planet 9 is complicated by the vastness of the search area and the faintness of such a distant object. If Planet 9 exists, it would be hundreds of times fainter than Pluto and could be anywhere in a search area covering thousands of square degrees of sky. Computer simulations suggest that finding Planet 9 might require surveying the entire sky to unprecedented depth, a task that could take many years even with the most advanced telescopes. Some astronomers question whether Planet 9 exists at all, proposing instead that the observed orbital clustering might be caused by collective gravitational effects of many smaller objects in the outer solar system. Others suggest that what we interpret as Planet 9's influence might actually be evidence of modified gravity or other exotic physics. The debate continues as astronomers search for definitive evidence. Comets present their own collection of mysteries. These dirty snowballs from the outer solar system carry pristine materials from the earliest days of planetary formation. When they approach the Sun, they develop magnificent tails of gas and dust, creating some of the most beautiful phenomena in the night sky. But comets behave in ways we don't fully understand. Some comets brighten unpredictably, some split apart for unknown reasons, and some contain materials we didn't expect. The European Space Agency's Rosetta mission to Comet 67P/Churyumov-Gerasimenko revealed that comet water has a different isotopic composition than Earth's oceans, challenging the idea that comets brought water to our world. But if not comets, then what was the source of Earth's oceans? Comet 67P also revealed that comets are far more complex than simple dirty snowballs. The comet has a rubber duck shape with two distinct lobes connected by a narrow neck, suggesting it might be a contact binary two separate objects that gently collided and stuck together. The surface is mostly dust and rock with patches of exposed ice, and it shows evidence of complex layering that records the comet's formation history. The comet's activity patterns don't match simple models of solar heating. Jets of gas and dust emerge from specific locations on the surface, often from areas that aren't receiving the most sunlight. The jets also vary in intensity and direction as the comet rotates, suggesting complex subsurface structures that channel gas flow in unexpected ways. Some comets develop multiple tails pointing in different directions, each composed of different materials responding to different forces. Dust tails are pushed by solar radiation pressure and curve away from the Sun, while ion tails are shaped by the solar wind and point directly away from the Sun. But some comets develop additional tails, or show variations that don't fit these simple categories. The phenomenon of comet splitting remains poorly understood. Some comets break apart gradually over multiple orbits, while others fragment suddenly and spectacularly. The forces that cause splitting might include thermal stress from solar heating, rotational stress from spin-up due to outgassing, or structural weaknesses inherited from the comet's formation. But predicting which comets will split and when remains impossible. Even our Sun, the star that makes all life possible, holds mysteries we're still unraveling. The Sun's corona, its outer atmosphere, is hundreds of times hotter than its surface, violating our basic understanding of how heat should behave. Energy should flow from hot to cold, yet somehow the corona maintains temperatures of millions of degrees while the Sun's visible surface is only about 10,000 degrees Fahrenheit. Recent space missions have begun to unravel the coronal heating mystery, but the complete answer remains elusive. The Parker Solar Probe, humanity's first mission to touch the Sun, has revealed that the corona is structured by magnetic fields in complex ways that channel and concentrate energy. But the detailed mechanisms that convert magnetic energy into heat remain under investigation. The Sun also experiences an 11-year cycle of activity that affects everything from radio communications on Earth to the formation of auroras at our poles. But we don't fully understand what drives this cycle or how it might change in the future. During certain periods in history, the Sun seems to have been much less active, corresponding with colder periods on Earth like the Little Ice Age. The Maunder Minimum, a period from roughly 1645 to 1715 when sunspots virtually disappeared, coincided with particularly cold winters in Europe and North America. But the connection between solar activity and Earth's climate remains controversial. Solar irradiance variations during the solar cycle are too small to directly explain significant climate changes, suggesting more complex mechanisms might be involved. Solar wind, the stream of charged particles flowing constantly from the Sun, creates a bubble around our solar system called the heliosphere. This heliosphere protects us from some galactic cosmic rays, but we don't know exactly where its boundaries lie or how it interacts with the interstellar medium. The Voyager spacecraft have crossed into interstellar space, but their measurements have revealed that the transition is more complex and gradual than expected. The shape and size of the heliosphere depend on the balance between solar wind pressure and the pressure of the interstellar medium, but both of these pressures vary over time, causing the heliosphere to expand and contract like a breathing bubble. We don't know the detailed structure of the heliosphere or how its variations might affect conditions within the solar system. The Sun's magnetic field undergoes dramatic changes during each solar cycle, completely reversing its polarity every 11 years. But the mechanism that drives this magnetic reversal remains incompletely understood. The Sun's magnetic field is generated by complex dynamo processes involving the rotation of electrically conducting plasma, but computer models still can't fully reproduce the observed behavior. Solar flares and coronal mass ejections represent some of the most energetic events in the solar system, releasing energy equivalent to billions of nuclear bombs in a matter of minutes. But predicting when and where these events will occur remains largely impossible. Space weather forecasting is still in its infancy compared to terrestrial weather prediction. The interior of the Sun remains largely mysterious despite decades of study using helioseismology, the study of sound waves traveling through the solar interior. These measurements have revealed the Sun's internal structure and rotation patterns, but many details remain unclear. For example, we don't understand why the Sun's core rotates faster than its surface, or how angular momentum is transported within the solar interior. Throughout our solar system, we find evidence of violent events in the past that shaped the worlds we see today. The Late Heavy Bombardment, a period roughly 4 billion years ago when the inner solar system was pummeled by asteroids and comets, left scars we can still see on the Moon and other airless worlds. But we don't know what caused this bombardment or whether similar events might happen again. The Late Heavy Bombardment appears to have been triggered by gravitational instabilities among the giant planets, possibly including the migration of Jupiter and Saturn through orbital resonances. Computer simulations suggest that these planetary migrations could have scattered large numbers of asteroids and comets throughout the solar system, leading to increased impact rates on the inner planets. But the evidence for the Late Heavy Bombardment comes primarily from lunar samples collected by Apollo astronauts, and some scientists question whether this evidence is representative of solar system-wide bombardment or simply local effects near the Earth-Moon system. Mars shows little evidence of Late Heavy Bombardment, though this might be because its surface has been more extensively modified by geological processes. The formation of the solar system itself remains partially mysterious. We know it began as a rotating disk of gas and dust around the young Sun, and we understand the basic process of planetary accretion. But the details are far from certain. How did Jupiter migrate inward and then outward during its formation? How did Earth end up with such a large moon? Why do some planets have strong magnetic fields while others don't? The Grand TAC model proposes that Jupiter migrated inward to within Earth's current orbit during the early solar system, then migrated back outward due to interactions with Saturn. This migration might explain why Mars is smaller than expected, and why the asteroid belt contains relatively little material, but the timing and details of this migration remain debated. The formation of terrestrial planets involved complex processes of accretion, collision, and differentiation that we're still working to understand. Earth appears to have formed through a series of giant impacts, including the impact that formed the Moon and possibly other impacts that delivered water and organic materials, but the timing and sequence of these impacts remain uncertain. Recent discoveries of exoplanets Mars worlds orbiting other stars Mars have revealed that planetary systems can be wildly different from our own. Some systems have massive planets orbiting extremely close to their stars, others have planets with orbits tilted at bizarre angles. This diversity makes us wonder whether our solar system is typical or unusual among planetary systems in the galaxy. Hot Jupiter's muck gas giant planets, orbiting very close to their stars, were completely unexpected when first discovered in the 1990s. These planets shouldn't be able to form so close to their stars, suggesting they must have migrated inward from more distant orbits. But the migration mechanisms that could move such massive planets without destroying them remain poorly understood. Some exoplanetary systems show evidence of violent dynamical evolution, with planets scattered into highly elliptical or misaligned orbits. These systems suggest that planetary migration and instabilities might be common during planetary system formation, making our solar system's relatively stable configuration somewhat unusual. The question of life beyond Earth remains one of the most profound mysteries we face. We now know of multiple worlds in our solar system that might harbor life: Mars with its subsurface water, Europa with its hidden ocean, Enceladus with its organic-rich jets, Titan with its complex chemistry. But we haven't found definitive proof of life anywhere beyond Earth. This absence of obvious life is sometimes called the Fermi paradox when applied to the broader galaxy, but it applies to our solar system as well. If life is common, if the conditions for life exist in multiple locations within our own planetary system, why haven't we found clear evidence of it? Are we looking in the wrong places, using the wrong methods, or is life far rarer than we hope? The search for life in our solar system is complicated by our limited understanding of life itself. We know only one form of life: the carbon-based, water-dependent chemistry that exists on Earth. But could there be other forms of life based on different chemistry, thriving in environments we consider completely hostile? Could life exist in the hydrocarbon lakes of Titan, using methane instead of water as a solvent? Could silicon-based life forms thrive in the high-temperature environments of volcanic worlds? Could plasma-based life exist in the magnetospheres of giant planets? These possibilities stretch our understanding of what life can be, but they remain within the realm of scientific speculation. Even defining life becomes problematic when we consider the weird and wonderful environments available in our solar system. Are viruses alive? What about self-replicating chemical systems that don't use DNA? What about complex systems that emerge from simpler components but don't reproduce in ways we recognize? As we explore our solar system, we may need to expand our very concept of what life can be. The detection of life elsewhere in the solar system would be one of the most significant discoveries in human history, but it would also raise profound new questions. Would extraterrestrial life share a common origin with Earth life, suggesting panspermia, the transfer of life between worlds, or would it represent an independent genesis, proving that life can arise through multiple pathways? The chemical signatures we use to search for life minus biosignatures like oxygen, methane, or phosphine might not be produced by alien life forms using different biochemistry. We might be surrounded by life that we simply don't recognize because it operates through mechanisms we haven't imagined. The timescales involved in solar system processes often exceed human comprehension. Mountains rise and fall on Earth over millions of years. Planetary orbits shift over hundreds of millions of years. Stars evolve over billions of years. Our sun will eventually exhaust its nuclear fuel and expand into a red giant, likely engulfing Mercury and Venus and making Earth uninhabitable. But this won't happen for another 5 billion years, almost a time span so vast it's difficult to grasp. Yet some processes happen surprisingly quickly. Asteroid impacts can change a world in minutes. Volcanic eruptions can alter climates in months. Solar flares can affect technological systems within hours. The solar system operates on multiple timescales simultaneously, from the split-second interactions of charged particles to the billion-year evolution of planetary atmospheres. Our understanding of these processes is limited by the brief moment we've been able to observe them. Human civilization has existed for only a few thousand years. Scientific astronomy is only a few centuries old. Space exploration began less than a century ago. We're trying to understand processes that operate over geological time using observations that span only a human lifetime. This temporal limitation affects every aspect of our solar system knowledge. We've seen Halley's Comet return only a few times in recorded history. We've observed only a tiny fraction of Jupiter's Great Red Spot's lifetime. We've witnessed only the most recent moment of Mars's climate evolution. We're like visitors who arrive at a vast, complex performance just moments before it ends, trying to understand the entire story from a few final scenes. The technology we use to explore the solar system continues to evolve rapidly, but it still imposes significant limitations on what we can discover. Our most powerful telescopes can reveal details on Mars that would be equivalent to seeing a basketball from a distance of several miles. Our spacecraft, despite their remarkable achievements, have visited only a tiny fraction of the interesting worlds and locations available for study. Even when we do send spacecraft to other worlds, the data they collect must be interpreted through our Earth-based understanding of physics and chemistry. We might be missing important clues simply because we don't know how to recognize them. The famous Viking missions to Mars in the 1970s included experiments designed to detect life, but the results were ambiguous and remain controversial decades later. Future missions will undoubtedly reveal new mysteries even as they solve old ones. The James Webb Space Telescope is already revolutionizing our understanding of exoplanets and might provide new insights into the formation and evolution of our own solar system. Upcoming missions to Europa, Enceladus, and Titan will search for signs of life in their subsurface oceans. Sample return missions to Mars, comets, and asteroids will bring pristine material back to Earth for detailed analysis. But each new discovery seems to raise more questions than it answers. This isn't a failure of the scientific method. It's a testament to the richness and complexity of the natural world. The more we learn about our solar system, the more we realize how much we don't know. As you drift towards sleep tonight, you might imagine yourself traveling among these mysterious worlds. Picture yourself floating above the methane lakes of Titan, watching the aurora dance in Jupiter's polar regions, standing on the icy surface of Europa, while an alien ocean moves beneath your feet. Imagine the view from Pluto's surface, where the sun appears as just another bright star in the sky, where the solar system spreads out before you like a vast collection of distant lights. From that perspective, Earth, our home, our oasis of life and warmth and complexity, appears as just one more point of light among many. But it's the point of light that gave rise to consciousness, to curiosity, to the questions that drive us to explore and understand the cosmos around us. It's the world that produced beings capable of sending robotic ambassadors to other planets, of detecting the chemical signatures of distant atmospheres, of pondering the deepest mysteries of planetary formation and evolution. The solar system's 100 unsolved secrets remind us that we are still at the beginning of our journey of understanding. Despite all our telescopes and spacecraft, despite all our theories and computer models, despite all our decades of exploration and study, we remain students of a cosmos that continues to surprise and humble us with its complexity. Perhaps that's as it should be. Perhaps the greatest gift our solar system gives us isn't answers, but questions, puzzles that challenge our understanding, mysteries that inspire our curiosity, unknowns that remind us how much we still have to discover. Every world we study reveals new possibilities. Every measurement we make opens new avenues for exploration. Every answer we find leads to deeper and more fascinating questions. The solar system that seems so familiar from our earthbound perspective reveals itself to be an endlessly complex and surprising collection of worlds, each with its own story, its own mysteries, its own possibilities. From the scorching surface of Venus to the frozen plains of Pluto, from the volcanic fury of Io to the serene hydrocarbon lakes of Titan, our cosmic neighborhood is filled with wonders that challenge our understanding and inspire our imagination. Tonight, as you close your eyes, you're traveling through space at 67,000 miles per hour on a planet that hosts the only known life in the solar system, orbiting a star that provides the energy for everything we know, in a system of worlds that each holds secrets we're still working to unlock. What a magnificent, mysterious neighborhood we call home. In the quiet darkness of space, among worlds both familiar and strange, among mysteries both ancient and newly discovered, the dance of the solar system continues. Planets orbit, moons rotate, comets journey from the outer darkness toward the inner light, and on at least one small world, curious beings look up at the night sky and wonder. Sleep well, wherever you are in our solar system, and may your dreams be filled with the wonder of worlds yet to be fully understood. May you find comfort in the knowledge that we are all travelers together through the cosmos, passengers on a planet that is itself a passenger in a solar system full of mysteries waiting to be explored. Good night.